Okay, so in this problem, we're told a 72 kilogram trampoline artist jumps vertically from the top of a platform with a speed of 4.5 meters per second. A, how fast is he going as he lands on the trampoline 2 meters below? And B, if the trampoline behaves like a spring of spring constant 5.8 times 10 to the 4 newtons per meter, how far does he depress it? So there's going to be two parts to this problem, an A and a B. But what we have going on here is we have this trampoline artist. And so he's going to start here. And we know he's going to jump downward. So he's going to jump up with a speed of 4.5 meters per second, and then he's going to come down and land on this trampoline. And so we know the trampoline's 2 meters below where he jumps. And so let's go ahead and start with A. So A is having us find how fast he's going to be going, or his velocity when he lands on the trampoline. So his velocity when he gets right here. And so the way we're going to use this is by using the law of conservation of energy, which basically tells us the energy here in the beginning has to be equal to the energy as he lands. And so the way we do that is by setting the initial kinetic and potential energy equal to the final, or the point at the end, his kinetic and potential energy there. So you need to know the formulas for both of those. So the formula for potential energy is mgh. The formula for kinetic energy is equal to 1/2 mv squared. So we know the energy in the beginning has to equal the energy at the end. So we're going to take U initial plus K initial, and it's going to be equal to U final plus K final. So let's just write these formulas in. So U initial is mgh initial plus 1/2 mv initial squared, and it's going to be equal to mgh final plus 1/2 mv final squared. So the thing you should realize is, well, you can set the parameters however you want, but we're going to assume his initial height is here. So we're going to set the base height to be at the trampoline. And the reason we're doing that is because if we set the final height to be the base, that means we can just say it's 0. So it's basically how far away is it from this final position, and if it's at it, it's just 0. So if this final height is 0, then you can just imagine like the ground too. So imagine this is the ground. So his height is obviously 0. So this whole term would go to 0. And then the initial height is just going to be where he starts. So he's 2 meters above. So the initial height in this case would be 2. And then the initial velocity, they tell us he jumps at 4.5 meters per second. And then notice all we have to solve for is V final then. So really we just have mghi plus 1/2 mv initial squared is equal to 1/2 mv final squared. And so as I just said, we know the value, so I'm just going to go ahead and plug those in. So notice that we have an m in each term, so we can cancel that. So we just have to solve now. So I'm just going to sub it in. So we know g is just a constant, which is 9.8 meters per second squared, times the initial height. So as I said before, that's 2 meters. So that's 2 plus 1/2 his initial velocity squared. So 4.5 squared. And that's going to be equal to 1/2 v final squared. So let me plug this in my calculator now. So 9.8 times 2 plus 0.5 times 4.5 squared. You'll get 29.725. Yeah, 725 equals 1/2 v final squared. Multiply both sides by 2, and then you would square root it to get rid of that. So you basically just take the square root of that. So you'll get V final is equal to, so I'm multiplying the value by 2, then square rooting it, and you'll get 7.71 meters per second. So 7.71, that's going to be the velocity when he lands on the trampoline. So right here, his velocity we know is 7.71 meters per second. So this right here is going to be your answer to A. And now let's go ahead and move on to B. Okay, so let's go ahead and do the second part now. So this one is asking if the trampoline behaves like a spring of spring constant 5.8 times 10 to the 4 newtons per meter, how far does he depress it? So essentially, the guy now when he's here, obviously he's going to push down on the trampoline, and we're trying to find how far it's going to stretch down basically. And so they give us the spring constant K. So they tell us that K is equal to 5.8 times 10 to the 4 newtons per meter. And so the way we're going to do this is it's basically the same thing as you did in the first part, except for you have to add elastic potential energy, which is a different formula. So the formula for that is 1/2 kx squared. So when we do this, we're still going to use kinetic and potential, but we also have to add this in now that we have a new element, right? We have this spring now, so we have to add that in. So when we do this and we sum them up, we got to make sure we include that. So if we add up all the formulas, so just like this, but we have to include this formula now. So we're going to have mgh. And so the way I'm going to label this is I'm going to call this point 1. So the point where he lands on the trampoline is going to be called 1. So I'll label those 1. And then the point at which is the most depressed, we're going to call that point 2, wherever that is. We don't know where that is yet, but we're going to call it 2. So obviously on the left side of the equation, we're going to start with 1. So mgh1 plus 1/2 mv1 squared plus 1/2 kx1 squared. So those handle the beginning, and then the end would be when it's most depressed. So mgh2 plus 1/2 mv2 squared plus 1/2 kx2 squared. So these are going to be the ones we have in our equation. So right off the bat, you should always figure out, just like we did in this one, which ones are 0. So remember, this one was 0. So which ones are going to be 0 in this one? So we want to keep it the same. So imagine this part is 0, and we're just going to say it's negative if it goes down. So it would be negative if it goes down. So the value we're going to look for is negative. If it goes up, it's positive, but that's not what we're dealing with right now. But keep in mind that this, we're going to call this value 0, just like we said this was 0 in the last one. So mgh1 now, since we're starting here and we're going to here, h1 is now 0. So this one would be 0. Okay, so we know that. And then the velocity in the beginning at that point, we do know. So he's going to be moving, so that's not 0. 1/2 kx1. So when you do elastic potential energy like this, or elastic energy, you need to know that x is basically how far the string will stretch. So in the beginning, before or right when he lands on it, it's not stretched at all. So we know x1 would be 0. So this one also goes away. h2 is going to be some height. We don't know what that is. So we leave that. We don't know what that is. So there going to be some height below. And then 1/2 mv2 squared, you need to know that this value is going to be 0. So because at the point where they're most stretched, he's not going to be moving at all. It's kind of like when you throw a ball up in the air and it reaches its maximum point, it doesn't move. So, right, because at that point, it's not moving at all. So v would be 0. So this is gone. And then kx2 squared, this is how much it stretches. So how far the string would stretch, sorry. And so what you should realize when you do this, that h2 and x2 are going to be the same value, because x2 is how far it stretches, and h2 is your position relative to the beginning. So however far we go down is however far the string stretches. So these two values are actually the same. So I can really replace h2, because notice these are two different unknowns, but if they're the same, we can actually solve this equation. So that's what you have to recognize, that this value and this value are the same. So you would have 1/2 mv1 squared equals mg, and I'm going to call this x2 now, just to fit the variables correctly, plus 1/2 kx squared. And yeah, so you're going to have this formula. I'm going to move this to the other side, because you should notice that this is going to be a quadratic since we have two variables missing like that. So this is going to be 1/2 kx2 squared plus mgx2 minus 1/2 mv1 squared equals 0. And keep in mind, we're solving for the x2, how far it stretches, the spring. And yeah, so plugging this in now, you should recognize that k, so this is just plugging in value. So 1/2 times k is 5.8 times 10 to the 4 times, I'm just going to call it x now, so x squared, plus the mass, which was 72 kilograms, I believe. Yep, correct. So 72 times g, just 9.8, times x2 minus 1/2 times the mass, which is 72 again, times v1, which was the velocity from the first problem, right? Because this is the same spot. It just We called this final at the end because this was our ending point, but now it's our starting point. So 7.71 equals, this is squared, sorry, equals 0. And so now I've already went ahead and simplified this. So this is about 29,000 x squared plus 705.6x minus 2139.9876 equals 0. Okay, cool. So now that we've got this, the way you can do a quadratic equation to solve this, I recommend just plugging it in your graphing calculator. And then you could just use, if you have a TI-84, you can just second trace and find where it crosses 0. And so when you do that, you're going to find two values. So the two values you find are, one's positive, one's negative. So minus 0.284 and 0.260. So you might be wondering, why is one negative, one's positive? So what you should recognize is x is the distance it stretches. And so we chose downwards to be negative. So if you see the negative here, let me go up here. So the negative means it's stretching down. So it goes minus 2.8.284 is the maximum it stretches in this direction. And then upwards, if it was the opposite way, it would be the positive value. But obviously, he's going to go downwards, so we know it's the negative value is the one we're looking for, not the positive. So we know that our answer is going to be this negative value here. So x is going to be equal to minus 0.284. So if we look exactly what they're asking, how far does he depress it? So he depresses it 0.284 meters. The negative is just indicating the direction it's in. So this would be meters. So that's why that is. So yeah, so minus 0.284 meters, that's going to be how far it's depressed. So this distance right here. But yeah, so that's going to be the answer to the second part. This was your answer to A. So your answers are right here. And yeah, hopefully you found this useful.